So, thank you. But I kind of want to do it. But I think too, it's kind of interesting as I watch the world, that large, kind of come around to MapReduce, or to do, let's say, that implementation of MapReduce is something that might have value. Google, Damon has kind of famously, for some workloads, at least moved well beyond those. I mean, we're going to talk about the transition from, let's say, the MapReduce era to now at Google, and why, what drove kind of these.
Sure. I mean, I think one of the things that has caused us to build infrastructure is we were often doing things out of necessity. So we would be running into problems where, we needed some infrastructure that would solve that problem in a way that could make it so that it can scale to deal with larger amounts of data, or larger amounts of request volumes and all these kinds of things. And there's nothing like kind of the necessity of needing to do something to cause you to come up with abstractions that help you break through the problems. So MapReduce kind of was born out of needing to scale our indexing system. We had a large number of phases, and they all kind of look similar in some respects, but we're doing slightly different computations. But if you look at them, we all wanted them to be, each phase to be robust, reliable, to be able to be parallelized across lots of machines, to be able to run on as many machines as we wanted to throw at the problem, and have that kind of happen automatically. And so that kind of was what started us down that path of having these scalable abstractions. And then over time, we kind of built other higher level abstractions that help us deal with other kinds of problems. So things like Bigtable came about because we had a lot of data sets where we had a particular kind of key for data, and then we had lots of different kinds of attributes of data that we would collect over time. So one example is, our crawling system has URLs and then a bunch of associated information about it. We have all the different versions of pages that we've crawled over time. We have other processes that are going around in the background and computing, what language we think this document is in, or how important we think this page is to read the page rank and so on.
Right. So it sounds like the applications kind of drive the engineering, right? I mean, is it a case of, is everything an iteration on something previous, or is it a case where you say, here's something we want to do, how do we build a system that can handle this?
I mean, in a lot of cases, we do kind of say, wow, we have all these problems, and we really like a system that addresses these 4 or 5 problems, because they're really key operational issues for us. Spanner, I think, is a good example. So Spanner is a system where, instead of having lots of separate instances of storage systems in different data centers around the world, we have one global namespace for data, and you can specify for a given piece of data how you want that replicated at a fairly high level. So you can say things like, I would like 5 copies of this data, 3 in North America, 2 in Europe, and then the system kind of takes care of that for you. And so if we need to decommission a data center or upgrade a cluster in Europe, the system has the flexibility to move it from one European data center to another while satisfying the constraints that people have.
All right, so what kind of workloads do you use something like Spanner for? I mean, that's kind of the epitome of what you might have thought computing was there. Like, it's in the cloud, it's similar. So it's really in one data center, but this is literally like, it's in.
Yeah, ironically, the first customer we decided to, an internal customer we decided to put on that was our ad system. Maybe not that. They're a pretty demanding customer, they don't want to lose any data. Yeah, so we used it initially and worked very closely with our ads team to get that. I think one of the things about developing infrastructure is that it's really important to work very closely either at yourself as a first customer of that infrastructure, or to work very closely with a small team that is going to be your first customer, because that rapid iteration you get of sort of feedback on which things are working well, does this interface work well, I like this feature, is much better than if you have a very kind of separated first use of this thing where you develop it in isolation.
All right, just so you get a sense of, this goes how much these systems scale across applications. So ads is the first thing to give a sense of where you might look at, what you might deploy in something like Spanner and Access. Then you build these things with the sense of, we might have one ideal kind of use case in mind, but really they have to be, easily kind of applicable to many things.
I mean, there's always this tension when building infrastructure. You could try to solve all problems for all people, and then you usually end up with something that's not very good for anyone because you've made too many trade-offs that make it so it doesn't have good performance or it doesn't have some attributes that you might want. So it's good to keep a few use cases in mind. And for Spanner, the main use case was people who want to deploy internal Google products across lots of data centers. And we're spending a lot of time prior to Spanner managing different instances of their data and kind of manually configuring, I'm going to run to this data center now, and I have another instance in this data center. It's just a lot of mental effort to keep track of. And so Spanner kind of removes a lot of that from a lot of it.
And then, so I was reading a blog post, a Google Research blog post the other day about image recognition of photos, and I thought it was just fitting. I was like, well, we found this new model from this competition with image recognition. We just happen to have a system in place for analyzing large-scale neural network data. I mean, can you kind of talk about? I mean, it's really kind of geeky at the data level, but can you kind of just discuss? I mean, so it's a big machine learning problem, right? That's something Google's been putting a lot of effort into lately. It seems like. Can you talk about the importance of machine learning and the importance of like the infrastructure, the systems as a part of that puzzle?
Sure. So. I've been working on a machine learning system for the last couple of years that is kind of using neurally inspired, biologically inspired neural networks. So the idea with this is you have very raw forms of data. It could be pixels of an image, could be, the spectrogram of a small snippet of speech. And you build up layers that each layer kind of builds on the layer below in terms of building higher and higher level representations of the underlying data. So, for example, in images, if you have one of these models, the first layer of neurons kind of learns to be receptive to edges in different orientations. So it might be very simple features like, is there an edge at this orientation here or one here? And then as you go up the hierarchy, the system automatically learns more complex features, things like corners or a little bit of invariance to exactly what angle something's at. And as you get to the top of these very deep networks, you end up with very high-level features, things like, does this image contain a cat? Which is one of the things we were working on in an unsupervised manner when we're training these networks. And we found neurons that have actually developed that learned to recognize whether or not an image contained a cat without ever being told what a cat was.
Right. So, I mean, it seems like, some would say it sounds like a lot of effort to figure out to recognize a cat. Where's the vision? Like, where do you take this, aside from image recognition, let's say, or aside from saying, I can search my photos by the animals.
Right. So I agree. A cat detector is not really a fine end goal, but really, these kinds of models are very useful in a whole bunch of different domains. So we've already deployed a better acoustic model for speech recognition on Android and iPhone now. That basically just drops our word error rate by a significant amount. Users really notice that the speech recognition is a lot better, and a lot of that is attributable to this neural acoustic model. The image recognition work is deployed so you can search for photos. You can now not tag photos, and you can say, show me pictures of beach or mountains or the Eiffel Tower. And the system actually is able to understand those things from the raw pixels and images. And then there's a lot of applications that we haven't deployed yet that are trying to do language understanding with these kinds of models.
Right. It's different when you're building applications. So if I look back at search, let's say, or some the kind of Google core products from back in the day, and then you start building these very consumer-facing products. I mean, not necessarily consumer-facing, but like consumers recognize when their speech app isn't working, right? When the speech recognition isn't there. Consumers, if you're doing something like a wallet, right? I mean, these transactions have to be kind of, I would imagine, of some consistency, right? I mean, what's the mindset, I guess, when you build it? Do you have a different mindset when you build one type of application versus another, and how you approach that?
Yeah, I mean, I think the kind of perceptual apps where you're trying to recognize speech and things like that, those are kind of different class of applications than ones like accounting or ad systems where you're trying to be very, be sure you're not losing any data. The perceptual apps actually have pretty nice properties in terms of, you can actually make errors in your calculations, and they're still pretty robust to that. So you could lose a machine that has part of your model on it and still able to do a pretty good job of recognizing things. But that probably wouldn't be the case in the ad system for a little while, actually.
All right. I mean, so there's a kid. I mean, it sounds like, I think part of it, like, you can't go back to, like, yeah, if I'm using Google Apps or using Speech or something, right? I mean, it kind of has to be there. Like, it's not like a snapshot in time, something to go back to, right? So, the real time. All right. All right. And then I'm thinking too, I was going to ask, we talked about the biological networks and the neural networks. I mean, so there's been talk here, like, we talked about AMD was on stage talking about, alternative server architectures and these GPUs and systems on chips. I mean, how important, do you consider the hardware at all when you build stuff, or, how important is it strictly like software?
Oh no, I mean, for these kinds of models, you're trying to build the best model you can, and often that means you need to spread the computation across lots of machines. And these models are very computationally intensive in terms of floating point kinds of operations. So the more capability a given machine has in terms of floating point operation per second, the fewer machines you need to kind of use to train a model or to apply models to images and so on.
So I mean, it sounds like not a big fan of the cell phone chips and servers, or I mean, is that?
I think for training these models, you probably want something that's a little more computationally capable, but for deploying them, it turns out actually running inference in these models, where you're essentially just trying to pass something through it and then have it say what's in it, that's actually a lot less computationally intensive. So there's a nice trade-off here where you can do lots of training of these models in the data center and then deploy some of them maybe to your cell phone or something.
Right. How difficult is it to get, we hear about, this discussion about a shortage of data scientists, let's say. We hear discussion about a shortage of distributed systems engineers, and then if you get into like the high performance computing space, supercomputers will talk about, this shortage of, real deep parallel programming. I mean, how difficult is it to get the people who can come in and build these things? Because it seems, it crosses so many fields that are all very, complex and difficult. So.
Yeah, I mean, I think each one of those specialties is hard to find people in, and finding people with expertise in many of those different specialties is even harder. But really, this is, a testament to the fact that these skills are in great demand, and our schools probably don't produce enough science and engineering kinds of graduates as they could. So anything we can do to encourage, more people entering those fields, that will help down the road a bit. But it's definitely an important issue.
I mean, how does that? I mean, when someone comes into Google as an engineer, is it a case of they already have a deep knowledge of this, or do you kind of say, hey, here's what you're going to be working on, and think it's a trial by fire sort of in the field?
I mean, we kind of try to pair new people up with areas or projects that are good for their current background, but you also want people to kind of learn the skills. Some people are happy to work in a particular domain or subfield of computer science for years and years. I personally like to kind of move around every few years just to kind of learn about new areas. So I like working in small teams where people on the team have very different skills than what I have, and that kind of banter back and forth and the ability to build something collectively that none of you could do individually is actually a really useful and valuable thing, because then you pick up some of their expertise, they pick up some of your expertise, and it's a really nice kind of plan.
Yeah, it seems kind of critical too in a day where it's not just, I mean, even a company like Google has so many different products that need to kind of work together, and then so many different devices or avenues for actually distributing it, right? So you need to have mobile development skills, right, or web or whatever, just kind of server side. So,
I mean, one thing I think is true is that if you have someone who's really good in one or a few areas, they can pick up something new pretty quickly, and that's kind of a hallmark of someone you really want to hire, because they can be very useful in a whole bunch of different areas.
Right. Do you ever look at engineering now at a smaller scale? I mean, do you ever look at, like, well, one thing I always think is interesting is seeing these startups, the Pinterests of the world, who came of age in the day of cloud computing and Amazon Web Services, and I mean, do you ever think back on like, what it would be like, like how I guess if you're starting today, you might, how you build something at not Google scale that can maybe grow to Google scale, right?
I mean, I think that starting something today actually has a lot of advantages compared to when we were the early days of Google, where we actually had to deploy hardware to run our software. And that's a really tricky thing if your service is successful and growing fast, because you often can't deploy hardware fast enough. And so you really have to end up doing a lot of software optimization and efficiency and redesigning of your systems in order to keep up with the demand. I think now, if you are using a large cloud provider, the Amazons or Googles of the world, you can essentially, design your system, and if you need 1,000 machines tomorrow instead of 100, that's a much easier proposition than if you have to sort of take 900 machines and wire Ethernet cables yourself.
Right. But I mean, is there a point where, clearly Google, do you see a cutoff point, or is there a time when a company like a provider like Amazon could actually grow to handle not Google but something, half that size? I mean, would you see a cutoff in terms of just the?
I mean, I think all these cloud providers take advantage of the fact that not all of their customers are going to need 10 times as many machines tomorrow as they do today. So they're essentially statistically multiplexing the demand and being able to satisfy everyone's potential for demand with a much fewer number of machines than if everyone all of a sudden went out and bought 10 times as many machines themselves.
All right. I think this is probably the last question. So I just wanted to ask, so we kind of talked about some of the stuff you're working on, which is, futuristic by most standards. What do you see next? You're right now, you're doing machine learning. What's on the horizon, or maybe what are the next applications where you're working on?
Well, I think this kind of perceptual machine learning is actually going to significantly change how people interact with computing devices. Devices are getting smaller. You're going to be able to assume that you have kind of a network connection to a big data center from your cell phone that's really reliable and high speed, and that really dramatically changes what you're able to do. You could, speech recognition is now good enough that I think you can start relying on it and building complicated user interfaces around just speech rather than having speech be something that you always have to fall back on something else. And that'll, I think, have pretty significant ramifications of special computing.
All right. How much